In this video, I would like to introduce a mathematical concept that is going to be pretty useful throughout this course. Okay, and essentially what I want to do is think about how we describe an area. Okay, so let me be a little more specific. Let's say that we have a situation like this, where I have some rectangle like so, and I want to describe its area. Well, there's a couple of different ways I can do it. So first of all, I might just tell you the area. Okay, so the first strategy is area is just the length times the width. So if I call one side the length and another side the width, then that's it. That's the area. Okay, so this would be a scalar, and the units are just meters squared, or something equivalent, inches squared, centimeters squared. But that doesn't tell me all of the information about the area. All right, so for instance, maybe I would want to know the length and the width individually. Maybe a long skinny area is different than a circular area, or some other shape. So maybe I would want to know more information about it. So one way to do that would be to tell you explicitly the length and width. Okay, so I could, for instance, have a length vector over here and the width vector on one side. So I could tell you both of those. Okay, so I could tell you length and width. Okay, so you could still figure out the scalar area from the length and the width, but this gives you more information. This tells you the shape, and this tells you that it's going to be, if not a rectangle, at least a parallelogram. And the units of each of these would be meters, but you have to give like the full vector, so 3 components for each one. So this is probably not the most convenient way to tell someone what the area is. Okay, so this one takes 2 vectors. And in fact, there's a name for quantities that have more than one direction associated with them. We call those quantities tensors. Okay, so there is, in fact, a mathematical structure for encoding 2 pieces of information about directions at once into, one quantity. You have seen an example of a tensor before. In 121, the moment of inertia, we treat it like a scalar, but in fact it's actually a more complicated thing. It acts like a tensor, and that's why rotation of complicated objects can be like really weird, is because of that tensor behavior. Okay, so are these our only 2 options? Do we just treat an area as the scalar with no extra information at all? Or do we have to go all the way to requiring this like more advanced mathematical structure to describe it as a tensor? Well, it turns out there's an in-between. Okay, so the sort of happy medium here is the third way to look at it, which is an area vector. Okay, so if you try to think, how can we talk about an area as a vector? What would the direction tell us? Well, you might have a couple of ideas. So one idea that you might come up with is, okay, well, I'll just pick one of these sides, and like that'll be my area vector. But the problem is you could have lots of different areas that all have that same vector. So for instance, I could rotate this, and maybe I rotate my parallelogram like this, and then it still shares a side. So I not only don't have the shape information, I also don't really have any information about the orientation. So that isn't really going to work. Lots of very different surfaces will have the same vector if I try to do that. And I run into the same problem if I pick any other vector that's in the plane. So for instance, if I went corner to corner, like that, I still run into trouble because I could still rotate the plane around that vector and have a bunch of different shapes. Okay, so the trick here is we want to have the same area vector represent, like, in some sense, the same area. All right, so the way we're going to do that is we're going to take our area like this, and the area vector is going to be perpendicular to it. Okay, so if I use that as the direction for the area vector, then even if I rotate the surface so that it's still perpendicular to that vector, the orientation stays the same. So the shape could be different. It could be long and skinny, or it could be a circle, or it could be, a square, or any other shape. But I still know which way it's facing. Okay, so that's the trick to use area vectors. The magnitude is just the area, as you might expect, and the direction is perpendicular to the surface. Okay, so that's actually a really nice thing to do. It gives us less information than our second idea. We don't know the shape information, but we do know how it's oriented. And it's also a little more compact than that second way. It doesn't require you to do any calculations if you want the area. You just take the magnitude. Okay, so that's great. If we have a flat surface, we can create an area vector for it, and we can use that for whatever it is that we want to use it for. But what if we have a curved surface? Okay, so suppose that we have some surface like this, and we want to represent area vectors for this surface. Well, it turns out what we want to do is just imagine breaking up the surface into little pieces. So each little piece is going to be basically flat if I make it small enough. And then I'll just have an infinitesimal area vector, which I'll call dA, for that piece. And as I split up the surface into other pieces, maybe I have a different one over here with a dA that's in a different direction. Okay, so the way to handle a situation where you have a curved surface is you just make the pieces really small, and then each one essentially looks flat, and you can do the same thing. Okay, and that's kind of nice now that we don't have to worry about the shape, because even if those were some sort of weird piece, because I can't cut nice squares out of a curved surface, that's okay, because all I care about is the magnitude of the little piece of the area and the direction.